So we've talked about forces very briefly in our force analysis from system schemas. And so now I want to start applying it to a number of things. And so let's uh, deal with this ball being thrown up in the air. We actually had a motion problem, essentially this same problem, a while back. And so uh, if you just think of a hand, so that'll be a hand, and there's a ball. Okay, so here's the ball, uh, here's the hand, and we're gonna go through uh, some motion. It's gonna, the hand, let's say you just kind of flip it real quick, just wrist motion only. Then the hand would move through that uh, thing, and the ball, it would go up, reach a high point, and then it would uh, come back down and be caught at that initial release point. So just a simple wrist flip of a ball. Okay. So we know what's going to happen. We know that it'll reach a peak altitude and stop moving and then fall back down to earth. So it's just kind of a stickman picture of the situation, the physical situation. So what we can do is we can draw a system schema of that. And so in our system schema, uh, here, system schema of the situation. You have a ball, you have a hand, and you have the earth. Okay, so I'm gonna put that over here just for ease of use. And so obviously the ball and the hand uh, have a contact force for some portion of the ride, and technically um, we're going to be real careful with this. Well, I can't do that. I'll have to. That should be a dash line because the hand is not always in contact with the ball. All right, so a dash line there. But the Earth, it never stops having that gravitational interaction. Even though the Earth doesn't necessarily touch the ball, the Earth is constantly attracting it by means of gravity, as long as it's anywhere near the Earth or on it. Whereas the hand is only periodically in contact with the ball. All right, and we would ignore its gravitational influence on the ball because it's too small to worry about. So what this means is if I make the ball my point of interest, so if that's going to be my system, the ball is going to be the system. Well, there are two force interactions on the ball. Okay, so this is the usefulness of the system schema, is to organize our thinking and to go, all right, I have two force interactions on the ball. Force is just another way to describe an interaction. That's what it really is. And we have various equations for various kinds of forces because they are various different kinds of interactions. But in general, force is a way to describe interaction. So is energy, but more on that later. So we have this system schema. And so if we wanted to, we could draw force diagrams for that system schema. So if I were to um, uh, do that, I would choose ball as the system because that's the interesting part of it. But before I do this force diagram, there's at least, well, how many phases of motion are there for this ball? Distinct interactions with the ball. Initially, is the ball moving initially? No, it's in the hand. And the hand flips it, so there's an acceleration that the hand goes through some, it moves the ball through some distance, imparting to it a force or making it accelerate, changing its speed. So I have the throw part of this. I have the flying, or what we would call in physics, free falling part of this. And then I have the catch part of it. So I have three distinct zones of motion, if you will, for this ball. So I'm going to use some graphical analysis here. So if we have uh, a velocity time graph, and let's also have an acceleration uh, time graph, and we'll key these things to one another. And so we have I'll zone these off here. So we have uh, a throw zone, if you will. And we have a catch zone. All right. And I chose to split up the free falling part, and it has a critical point in it. So let's think about, so initially the ball is at speed 0 because the hand's not moving. And then we could assume that the hand applies a constant force, okay? So it would change its speed in a uniform way. We can make that assumption, and it's not a bad assumption. And as soon as that ball leaves the hand, what happens to its speed? We, it starts immediately, as soon as it leaves the hand, we know the speed of the ball immediately starts decreasing. It starts with a really high speed given to it by the hand. Talk to the hand. All right. And then its gravity immediately starts chewing into that speed. So immediately it's at a high speed here, whatever this is. But then it starts decreasing in speed, and it will, at a high point, hit 0 speed. And then it will turn around, its speed will be negative until it's caught, which it'll have an abrupt stop there. So this is our graphical analysis, one-dimensional motion of this. And then during that time, during uh, the throw, there was some positive acceleration that the hand was given to the ball. And forces produce accelerations. And either those accelerations are large enough to change speed or they are not. All right. Those forces could also change direction, which means you would be changing the velocity, but not the speed necessarily. Little subtleties in it. Well, as soon as it leaves the hand, now gravity takes over. All right, so we had some positive acceleration here, and then G takes over, and then as soon as it hits the hand and comes to a stop, then it has that profile. So this is its motion profile, and forces produce motion. In fact, Newton's first law, what is it? An object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by an outside force, meaning unless some outside force changes its velocity or its speed. All right, those are related but different things, speed and velocity. All right, so we've profiled that. So that means I have a couple of uh, things to consider about the ball. All right, so the ball has mass. All right, and gravity. All right, F equals ma, and in this case, when a is equal to g, this is the weight of this ball. Now, if I let me redo this. I have the force of gravity, Earth on the ball, and that equals mg. Okay? So the gravitational force that any object is under is going to be the mass of that object times little g, which is the field strength, gravitational field strength of the Earth, or what we sometimes call acceleration due to gravity. Technically it's a field strength, it's some newtons, 10 newtons per kilogram, but we also talk about it as being something that accelerates. All right. So during the throw, there's some other force on it, and that's just the force of contact of the hand on the ball. And in this phase, acceleration is upward, and in fact, the change in speed is greater than zero. It's one way to pay attention to this during the throw. All right. So we have that first part of the acceleration, and during that phase, the sum of forces, I'm going to have that up force of contact of the hand on the ball minus the down force or the weight of this thing, and that's going to equal mass times acceleration. This is the sum of forces. So when we sum the forces, that is a Newton's second law statement about the forces. I've modeled the forces during the throw. So if I knew the mass of the ball and I knew what its acceleration was, let's say I knew what its speed was when it leaves the hand, that means I know what its change in speed was. And if I know how long it took for that to happen, then I would know the actual acceleration. And so you saw with the video analysis that we did, we could film this and figure out what the initial speed of the ball was using letting the camera do the work for us. Okay? Or we could make up numbers for a problem like we tend to do in books and say, if it left the hand at this speed and it took a tenth of a second for that to happen, you now know the acceleration. If you know the mass and acceleration, you can plug and chug and know, oh, the hand delivered, this many newtons of force to the ball. All right, so, but we're just modeling it generally. Okay, having givens would be a different part of the puzzle. Now, during free fall, we have other things to consider. So we still have the ball. Let's do this. I'm going to change colors here to keep things straight. Still the ball. It always has this mg part to it. So we'll, for sake of space, model it that way. And let's talk about the part where the speed is not equal to zero. Because if you look at this, the free fall graph, most of that downslope, the speed isn't zero. All right? So let's just talk about most of the motion of the ball where the speed is not zero. Well, during that entire time, acceleration is negative, meaning the change in speed is negative. And so when we go to sum these forces, the sum of forces for this part, well, I have no upward force, right? What I have is I have minus mg. Now, why is it minus? It's down. If you draw a force as a down force, and unless you specify otherwise, that's negative. And necessarily, any force that's pointing opposite of a down force would be positive. You could redefine your y-axis if you want, make up negative and down positive, but you can't have an up be positive and a down be positive. There has to be a symmetry there. So we'll just stick with the standard issue. Now, according to this, the sum of forces, there's one force on it. When it's in free fall, we're ignoring air friction. It's just got that one force. It's got the weight force due to gravity, all right? And so according to Newton's second law, which is the sum of forces idea, superposition, meaning you add up all the forces on something, that has to equal its mass and acceleration, all the forces acting on it. We're ignoring the reality of air friction for simplicity, just gravity acting on it during the free fall. So that means mg, negative mg, equals ma, and I think it's not hard to see that a is going to be equal to minus g. This is an important thing right here that we get to, and you'll read it in a textbook, and usually people go, okay, and then you'll forget it when it comes time to solve. Little g, acceleration due to gravity, or the field strength of Earth's gravitational field, is a 9.81 meters per second squared, or more formally, it's 9.8 newtons, which is a unit of force per kilogram, a unit of mass. That's just Newton's second law, force per mass. That's what acceleration is from a dynamics perspective. From a kinematics perspective, acceleration is delta v per delta t, or what we call acceleration, little a. But from a dynamics perspective, the cause of motion, it's a force per unit mass. That's what an acceleration is. So we get this for the non-zero speed part. And you would get the same thing for when speed is zero. So this also works when the speed is zero. And you hopefully recognize that this entire time from here to there, even at the zero spot here, only gravity is causing the acceleration. All right. So basically, while the hand's got it, the hand is causing all the acceleration. It's overcoming gravity. And the heavier the ball, the more massive the ball, the harder it is to change that speed, and vice versa. And then during free fall, it's just changing speed due to gravity. There's one acceleration in town. So this rule down here covers a lot of ground for us. Now, what we can do, we can simplify this a little bit. And so the force of contact of the hand on the ball, okay, which is also the sum of forces, is going to be ma plus mg, or what we can say here is that the sum of forces equals mass times acceleration due to some causal interaction like a hand, plus the acceleration due to gravity. So guess what? This will work at any point in the motion of the ball. When the hand's no longer providing an additional acceleration, then a is zero. And it's just g. All right? But it would have a negative part on it, but the sum of the forces is just going to be mass times acceleration. And really, all we're doing is summing acceleration. So there's a sum of forces, on your left-hand side of your equation, and you would expect, since forces produce accelerations, there would necessarily be a sum of accelerations, or a way to understand it in that fashion. Okay, so that's using graphical analysis to or marrying up everything we've done in the course so far with our force understanding, which we're going to keep expanding for the rest of the course. It's all about forces and energy, which energy is force times distance, or what we call work. We'll get into that soon enough. So that's uh, bringing our first couple unit stuff of one-dimensional motion into the system schema force diagram puzzle, Newton's second law, which is a huge deal for physics, obviously. So that's exhibit 1. What I want to do now is go over a thing called the Atwood machine. So this Atwood machine business, so I'm going to have a ceiling here. And from this ceiling, I am going to hang a rod that contains a pulley. And hanging off that pulley are two masses connected by one rope. I'll call them mass 1 and mass 2, and I will put the ground beneath them. So this Atwood machine business, and so let's give some parameters here. Let's say that mass 1 is greater than mass 2. What will happen if mass 1 is greater than mass 2? Not all at once. Mass 1 will fall towards the ground, and since mass 1 is falling towards the ground and it has a rope connected to mass 2 will do the opposite. Okay? And so hopefully you would also expect that, well, mass 2 will fall to the ground because gravity is accelerating it, but because of this connection that it has with mass 2 through the rope, I don't expect it to move at gravitational acceleration because there's an offset here due to the other mass. So what we'll do is we can generate a system schema for this. So I'll do that. And so we have mass 1, mass 2, the Earth, and I'll just use the rope. Pulley, we'll get into roundy motion and force interactions towards the end of the semester. But I'm primarily interested in the rope, which will have a tension in it, correct? If you hang something on a rope, there's a tension in that rope. You could measure that force if you had a scale. So think of the the produce scale at the supermarket. That's a spring scale. It's essentially a twisty rope, and it measures. You can measure force with it. So the rope is in contact with the mass, both masses, and the Earth is exerting a gravitational force on both masses. And I'm going to ignore the gravitational interaction that we have with the rope because the rope's not going to fall to the ground necessarily, at least in the same way that the masses are. We're just going to ignore that for simplicity. And so what that means is I can talk about mass 1 and mass 2 systemically uh, and come up with a force explanation, a force diagram explanation, and therefore a force set of equations explanation for this situation. Okay, so if I talk about mass 1, I'm going to have two force interactions to pay attention to. So mass 1 has its weight force down, and it has what I'm going to call tension. I'll just use a big T, and I'll kind of put in words here, tension. I don't mean to put that as a subscript, just that's a side note. T for tension, as opposed to force of contact or rope on block. Okay. You'll get some more practice with that, but for this, I want to try to make this more practical to the way you'd actually solve a problem. And conventionally, when we talk about a rope or something that has tension in it, we just use a big T for tension when we're talking about forces. All right. So mass 1, though, it's going to be accelerating downward. Okay. That's going to be a minus ma for mass 1. Now mass 2 has the same two force interactions. It has the rope force or tension force as well as gravity, except instead of it being M1G, it's M2G. But tension, is tension going to be the same or different? How many tensions do we have in one rope? Just one, right? Tension's not going to change in the rope. There can be one tension. So this is a bonus here, especially for equations. We'll have two equations with the same unknown, all right? And that's going to be a bonus for us. But mass 2 is accelerating upward. So if I sum the forces on mass 1, I'll just put that there, then I'm going to have a tension up that's positive minus the weight, or M1G, and that's the sum of the forces. So there's two forces on it. I sum them using signs and directions as shown, and that has to equal MA, but in this case, it's a minus MA because that acceleration is negative. So F equals MA, or the sum of forces always equals MA, but if your A is downward, if it's negative, you put a minus sign on it. All right? Now, the sum of forces on mass 2, using that subscript, same upward force of tension. Gravity is going to still pull the weight, or create the weight force on mass 2. But this time, it's a positive MA because A is upward. Well, T equals T, correct? So that means M1G minus M1A, that's from the first equation, will equal M2G plus M2A. I need to go back and put some subscripts. So excuse me while I correct what I left out initially. There we go. Now that's a correct set of equations. So we've eliminated tension in the rope, and now we have this new equation that we can do some stuff with. So what I can do is I can get all the terms with G on one side and all the terms with A on another, and come up with something here. So let's get A over on the left-hand side here. Or we can leave G over here, I guess, for sign. So M1G minus M2G will equal M1A plus M2A. Going to bring things up over here. Hopefully I'm going to flip my left and right hand sides around. I didn't change anything, but put the right on the left and the left on the right. Same equation, same balance. So if I solve this for A, well, you'll notice here, if I can do a couple of things. Well, for one, I can pull out the sum of masses. Over here, let me erase this, got ahead of myself. I'm going to have a difference of masses associated with G, which means my acceleration will be m1 minus m2 over m1 plus m2 times G. So we have this interesting new version of acceleration, at least for the Atwood machine, where a difference of mass relative to the total mass of the system, it's going to be some fraction, right? Won't the difference of two masses always be smaller than the sum of the masses? It's kind of necessary, right? Which means I'm always going to have a fraction less than 1, which means in this interaction, I can't get anything larger than G by interfering with gravity. Gravity causes one thing to move, but something else is holding it back a little bit. There's a tug of war literally going on there due to mass. And so one mass wins the game. So it's like a tug of war game. If everybody in the class but me got on one side of the rope, unless, I took some super soldier formula this morning, you guys are going to win. All right. I'll put up a good fight and then I'll give up. All right. So same thing, except this is gravity doing the pulling instead of people doing the pulling. So we have this Atwood machine version of acceleration. And one way to, F equals ma is how we got to this. And often you'll use forces to determine things like acceleration or speed. All right, so this is a classic. Every physics textbook in the galaxy has some treatment of the Atwood machine. All right, and this helps us solve all sorts of problems.